Okay, so this is the second half, and we'll actually talk about specific programming debugging tools this time. So yeah, so last lecture was focused more on the general question of how do you actually debug programs? How do you think about debugging? What is the general approach? And like I said, it's generally independent of the language that you're using, although there were some specific language things that we went through about how to enable and disable code in C so that you can turn on and turn off different parts of your program. So this time we're going to focus on specific tools, specific approaches for debugging C and IA32 assembly programs in CS24. So it's much more specific. And we'll talk about GDB, very briefly touch on DDD and Valgrind. Okay? And Eclipse was mentioned. Eclipse has an integrated debugger. If you're using it for C, is that right?
No, I used to use it for Java.
For Java, yeah. So Eclipse definitely has really good Java integration. I believe that there's an Eclipse C++ module as well, which I don't know if you would want to try using that for doing your C programming, but it also integrates GDB into the visual debugging facility. So I'm sure it's not as strong as the Java debugging, but you can at least give it a try, I suppose. Okay, so yeah, last time we talked about these points. So watching a program fail, that's one of the reasons why you need to be able to reproduce failures. Another reason is so you can zero in on the cause, sort of enable, disable different parts of your program, feed it different inputs, try to narrow down the issue, and also testing if you actually fixed it. I mean, once you make a fix, you need to be able to see if the failure goes away. So these are all reasons why you had to be able to reproduce failures. Okay. So the debugging tools are really focused on watching your program execute in less intrusive ways, as opposed to adding debug printouts, which we've all done. I mean, I don't think anybody in here didn't do that, or at least they didn't admit it. So we all do that. That tends to be a very common approach. But like I say, it's not always possible, especially if you have a situation like IA32 assembly. How do you add debug printouts to assembly code? So GDB is the GNU debugger, and it is designed by the same people who wrote GCC, G++, AS, and all those other fine tools. So it knows how to work with them very well. And it also happens to know the source languages that you're working with. So it will display C code as C code, C++ as C++ code, and so forth. And when you refer to expressions, when you type expressions into GDB, you can type them in the language that you're using, and it will actually understand those things. So the idea is that you load your program into GDB, and when GDB starts, it loads the program into memory, but it doesn't start running it yet. Because you may have to do some setup, like adding breakpoints, if you know that there's issues that are occurring at particular locations. Once you've done that setup, then you can run the program in the debugger to figure out exactly what's going on. Okay. So, yeah, the compiler doesn't normally store the variable names and function names and all the comments and everything that you so carefully write, because the machine doesn't care, right? The machine just wants to execute the machine code instructions. So a lot of information is thrown out, but the reality is you need that information if you're going to be doing any debugging, because you're a human being and you're not going to know what address is meant or what variable corresponds to what address or function address, things like that. Okay. So the thing to do is to tell the compiler to include this information when it's compiling. Okay. Remind me what variable name goes with this address and things like that. So the way you do that is specify -g to GCC, G++, AS, they all take it, and that will cause the compiler to record a lot of useful debugging information in the binary file, okay, including correlations between machine code instructions and the source line that generated those instructions. Okay? And then GDB can use that to display what line of code is being executed as you debug your program. Yeah?
What would be the point of doing this to AS if you already have assembly?
Well, that's a good question, but there's a lot of stuff that AS takes that the machine doesn't care about, like labels, like human readable label names. You can actually create variables that AS assigns an address to so that you don't have to worry about the address itself. There's a lot of things like that AS takes care of for you, and so you'd like the debugger to expose that information as well. Yeah, another thing that you need to do is turn off optimizations. Now, I'm pretty sure GCC turns off optimizations by default, But if you happen to be working in a situation where optimizations are turned on for the default build, then you need to make sure that you turn them off. Because the compiler will frequently reorder instructions to maximize the use of the processor resources. Okay? And so since that's the case, you need to make sure that you tell it not to do that, because it gets really bewildering to debug a program when you take a step forward and then you try to take another step forward and it actually goes back, because instructions for particular lines have been interleaved with each other. Okay? So yeah, and for that you specify capital O0 to GCC as well. Okay? You can make your makefile do this. In fact, we frequently do this in the makefiles. I don't know if you've noticed this. If you haven't, then you can certainly add this yourself. So C flags equals dash lowercase g dash capital O0, and AS flags equals dash lowercase g. And this will cause the makefile to include these options when it invokes GCC and the assembler. So when you do that, of course, you need to recompile everything, because any object files lying around are going to be compiled with the old options. So you need to do a make clean and then rebuild, and you should see the dash G's in the commands that are issued by make. Okay, so just be aware of that. You can use that to double check that you're generating debug information. You need to do this if you're trying to debug and you're not getting it to work properly. Okay, and of course, like I was saying, we try to include this in the make files that we give you, because we have this kind of suspicion that you'll probably need to debug things. So we try to make sure that it's set up for you so that it's easy to do. Okay. So once you've actually done that, one thing you'll notice is the program is larger. The binary will be larger because it's got more information in it. But then you can use GDB and that information will be displayed. Now here's the classic, right? My program crashes and I don't know where and I don't know why. I run it and I get a segmentation fault. Okay? So here's an example, numMain. In fact, let me just show you. You've got this program numMain. So let me go to the terminal and I will go to the CS cluster. Woo! SSH scimitar. Okay, and then CD CS24 Debug2. If I remember correctly. And in here, I have a program, a very simple program. This is going to be the example that we use. So let me see, vi numlist.h. It's a very simple linked list. So you have a node struct with a value, it stores an int value, and a pointer to the next node. You have a list struct, which stores a pointer to the head, a pointer to the tail, and the number of nodes in the list. Okay. Hopefully everybody's familiar with this. Init just sets up a list struct to be an empty list, so it initializes head and tail to be null, sets the size to 0. Add_num appends a number onto a list, an existing list. Empty clears out the contents of a list. Print list prints the contents of a list. Reverses the elements in the list in place. And that's it. So empty is the one that you use to actually free the contents of the list as well. So init and add_num should be calling malloc, and empty, actually init doesn't. Only add_num calls malloc, and empty calls free on the things that you allocate. It's a really simple program, right? This is the header. So then we'll also look at numMain.c, because this is where we use it. And you'll notice we have a main, we have a list struct, we initialize it, we add 31415, you may or may not notice those numbers. Print out the original list, and then we reverse it, print the list again, and then we add more numbers, 92654. Then we print out the original list, reverse it, and then at the end we empty it. So pretty simple, right? Not a very complicated program. So if I compile this, make, and then I say numList, oh, I did a bad segmentation fault, right? So what's going on? I have no idea, right? I have a bug. Now I haven't shown you numlist.c, and you can probably tell from the file names that I have varying kinds of bugs up there to show you all. But anyway, I have a bug in my program, and it's causing a segmentation fault, and I just do not know why. So how do I diagnose this issue? Well, the easy thing to do is just run it in GDB. Don't tell it any breakpoints or anything magical like that. Just run it, and then it will tell us exactly where it was when it crashed. Okay? So you say you gdb num main loads up, then you type run, and it goes, and then it crashes. And it tells you exactly what line it was on. So in this case, you get a sig_v, a segmentation violation, because it accessed memory that it wasn't supposed to. And look, wow, it tells you exactly what file and what line. How much nicer could it be? Okay, so GDB already saves you a bunch of time because now you can figure out exactly what line of code it was on when it crashed. Okay, so this already should be like a huge benefit. So if I go back to my example really quickly, and I say GDB num main. Okay, so that's the debug output. Notice it just says reading symbols from the file, right? So that I know that it's loaded the debug information. Then I type run, and it says, hey, you have a crash. Okay, so now I can actually look at the information. So for example, typing list to see what code is this in. Oh, it's in add num. Okay, not only that, but you can see I get information about what's the address of the list, what number was I adding.
List has to do with the fact that you're listing code and not the actual.
Yes, even though I'm working with the list data structure, but don't let that confuse you. The list command lists the code that you're debugging. Yeah, that's a very good point.
And it goes to the point where the error was?
Yeah, the crash was on, well actually it's centered around it. If I type list again, now I'm not going to go through all these details because GDB has a help feature and you should use that. But yeah, the first time you type list, it will list like 5 lines on each side of the line that it's currently on. Now, anybody have a guess as to why this is crashing? Yeah. Notice I'm adding the 3. This is the very first element I'm adding to my list. Yeah. Yeah, remember what I set up with my head and my tail? I initialized them to null because the list is initially empty. So then I come in here and do what?
You're trying to get the tail of something.
Yeah, list arrow tail arrow next, and we die. So I'll just show you this as well. Print list. So list is a, oh yeah, that's right. I should actually LST. I'm going to capture all my errors for posterity. Anyway, so you can see that's a pointer, but I can do things like this. Dereference the list pointer and print out the list object. It will actually print out the contents of the struct. So the head is null, the tail is null, the size is 0. Ah, okay, I have a huge bug right here, right? So things like that, it becomes really easy to debug issues like this, crashing issues, because you just run it in the debugger and it stops at exactly the point where it crashed, and then you can actually look at the program state. You have so much more information about what could be going on. Okay? So this is really valuable. This by itself will save you a bunch of time. Okay? So yeah, you can look at the surrounding code, just like I showed you. List will print out the code, and we already did the diagnosis and figured out what the issue was. Oh, I forgot to check if the list was initially empty. Okay? And you can do other things. Wow, this is funny because this is exactly what I was doing. So print list, print star list will actually print out the contents of a struct, which is really helpful. List arrow tail, print n. You can look at what n was. That's the new node that was created. Hey, that thing was allocated properly. Print star n. That dereferences the pointer, so it'll print out the contents. So value is 3. Next is null. That's the way it should be. Right? So this is really cool. GDB also understands when we give it C-style syntax. Okay? This is a very common thing as well, like especially in the CS11 C++ track when you're debugging long linked lists, you can say list arrowhead, arrow next, blah, blah, and then dereference it to see what that node looks like. Okay? Questions on any of this? Very, very helpful stuff. Okay? Now, you can also see the exact call sequence by typing where, and obviously my program is very simple, so I only have 2 levels in the call stack, but you can actually do this for your programs as well, and you may see 5 or 6 levels. If you're debugging a recursive function, you may have a lot of levels, but you can use this kind of thing, and notice it prints out the arguments at each point along the way as well, and what line it was invoked on as well. Okay? Very, very helpful. I can't tell you how helpful this is. It's just so nice. Okay? Now, next thing that you can do is you can also set breakpoints. And the idea is that when you reach the breakpoint, the program stops automatically so that you can look at what's going on. Okay, and this is usually for situations where you have a suspicion that you have a problem at that location. Okay? You can only set breakpoints when the program is stopped. You cannot set breakpoints while the program is running because, it's doing stuff. Okay? Yeah, so let's say that we fixed the previous bug, but we still have this strange behavior. Okay? Remember that the program added 31415, and then reversed it, and then reversed it again. And then you added more digits, right? 31415, 9265 something, right? So 92654. So it adds those things, but notice that we're missing some digits now. Okay? So now we think, okay, well, the complicated thing we do is reverse the code. Now you could always try taking out reverse, see if the problem still occurs, and then put it back in and see if it still occurs. So you can do something like that. Okay? So you can set a breakpoint on reverse. And then you can go through the code and see exactly what happens. Okay? So I'll show you guys this really quickly just so that you get a sense for what you can do. I'm going to exit GDB, and then what I'm going to do is go ahead and, what is this, numlist.c. We can go ahead and fix this really quickly. If list tail not equal to null, then do this. Actually, I don't want to use that for now. Do I need to do anything else? I'm slow tonight. So that appends onto the list. Maybe I should just copy it. Okay. Oh yeah, otherwise, list head equals n. So that's the obvious thing that I need to do. By the way, do we have a bug in empty? Remember, empty cleans out the contents of the list. Do you have a bug in the way empty works? Yeah. Yeah, so notice that we free memory and then we access it. Is this going to crash? Yeah? Who says yes? Yeah, that's the right answer. Maybe is the right answer. If you're lucky is the right answer. I have a feeling this will not crash. I don't think it crashed last year when I ran it. Okay. Anyway, seriously, I'll show you.
Because if no one else wants that.
Yeah, if nobody else has touched that memory location in between the time that you freed it and the time that you access it, the values are still there. Oh, how do you find these bugs, right? It's horrible. So anyway, let me copy in the copy numlist bad2 to numlist.c. Okay, so we fixed our bugs magically. I'm really good. Make clean all. We build this num main. Yeah, so this also fixes the reverse bug, but let me show you really quick how to do that num main. So load up the program, then you say break reverse, and then you say run, because the program hasn't actually started running yet, and it'll run it until you hit reverse. And then you can do things like list, see what the code is. You can do step, so you can run through your code like this and see exactly what's going on. So very useful to be able to see your program execute. And along the way, you can do things like, okay, print cur, print star cur, print star prev, things like that. So it's very helpful to be able to do this kind of thing when you're debugging a program. Okay, let me go back to the prezo. All right, so yeah, every time you reach the breakpoint, it stops. Okay, and then you can do various things to look at the code. So you have several options. Step and next both take a step to the next line of code, except the step goes into functions and next steps over them. Okay, so a little bit different. If you need to descend into a function call because you're not sure if the bug might be in there, use step. And if you aren't worried about the function, or it happens to be a library call or something like that, use next so that you don't end up in some strange code that you didn't write. Continue is also, you can use that to continue on running until the next time you hit a breakpoint, or the program terminates, or it crashes, or whatever it decides to do. Okay, so these are very helpful. Now, yeah, so you would go ahead and use this to go on debugging your program. Okay. So, yeah, you can set breakpoints in several ways, either using a label, function name, class name, colon, method name if you're in C++. You can use file name, line if you want to stop in the middle of a function, which is sometimes helpful, a little bit annoying though. And every breakpoint has an ID, and you can use these to enable and disable breakpoints as well. Okay, so break reverse, and the debugger comes back and says, oh, that's breakpoint 1. And then you can disable 1 or enable 1, and then if it's disabled, it won't stop there when it hits it. Okay? Now, all of the commands can also be abbreviated, which is really helpful. So you tend to turn into this mode once you get familiar with GDB. So R for run, B for break, cont or C for continue, S for step, and so forth. Okay? And print, P is a lot easier than typing out print all the time. Okay? And there are a lot of other commands as well. So if you are unsure, use help and then the command name, and that will give you more information about all the options for the command. So for example, list has a lot of options, what code you actually list. And so you can type help list to get more information than you might expect on how the list operation works. Okay? Let's see, any questions so far? All right. Let's see, now there's a graphical front end to GDB called DDD, and you started with DDD and then the program name instead of GDB, and it doesn't really give you much more than just a bunch of buttons you can push instead of commands to type. In fact, a lot of the buttons say exactly what the commands are that they would do anyway. So step, next, cont. Step I is nice, take a certain number of steps. Next I, take a certain number of steps. Up, down, you can use that to traverse the call stack if you need to look at the calling function to see what's going on. Things like that. So you have all of these options. You can use them all from the command line just as easily. But if you like buttons and stuff, there you go, right?
Does it offer you the functionality of seeing your code and like the thing hopping around?
No, it does not. It does not do visual debugging. So like why people would use this, I really don't know. Just use the command line, right? You can see the GDB prompt in there. It's just going to show the same output that you could type anyway. Woo! Awesome, right? So yeah, I don't really know exactly why someone would use this, but some people seem to like it. Okay, yeah. So basic hand holding. Yeah. So I would advocate going for the command line directly and just bite the bullet and learn it, or use something really awesome like some visual editor. But I don't really know a good one for C except for Visual Studio, and most of these labs won't work on Windows. So okay. Anyway, you can also step through IA32 code, okay, which is interesting, but the print expressions change a little bit because you don't type % register name like we do on IA32 in the AT&T syntax. You type $ register name. Now, if you want to print out a particular register that holds a pointer or an address, notice you have to put a cast operation in front of it. The int star part is what you're saying. ESP, treat the ESP register as if it were holding an int pointer. And then the star in front of it is saying, now dereference that int pointer. Okay. And so that would show you the value that's actually stored where ESP is pointing. So it would show you the top of the stack. Pretty lame. I don't like it. But that's the way it is. And if you wanted to see, well, what's above, what's just below the top of the stack, then you say ESP plus 4. Cast it to an int star and then dereference it. Okay? So just be aware that there's some grungy stuff that you have to be aware of when you are debugging assembly code. There's also info reg or info registers or ireg if you really don't want to type very much. And that basically dumps all the registers out in one shot in both base 10 and base 16. So that's really nice. You can use that easily to see what all the registers are when you're debugging. Okay? Now, a few other things. GDB can also be set up to display things. You can say display and then a particular expression. It'll show it after every line. Sometimes that can be very useful. I actually mentioned that in the write-up for the solutions for the third assignment because I found that helpful when I was debugging the run length encoding code. And I also will have a cheat sheet for you all to look at on the Moodle. I can't believe I haven't already put it up there, but I'll put it up there tonight or tomorrow so that you can look at that as well. And it'll contain a whole bunch of useful commands on GDB besides the ones that we've already talked about. Okay. Now, one issue. GDB is great for finding crashing bugs, and it's great for watching assembly code execute, and it's also really good for watching C code or C++ code execute as it runs when you need to debug things. But there are certain kinds of issues that GDB is not good at finding. I have them listed here. There's a water here, which I will take advantage of. But so accessing memory that you freed, right? How does GDB help you debug those things? It really doesn't, especially if it doesn't crash, right? Freeing a memory block multiple times. Well, GDB will tell you that, the program crashed on a free, and you may even be lucky enough to know that you already freed it, but how do you know where it was freed the first time? Accessing memory through an uninitialized pointer. GDB can't really help you with that either. So let's go back to our program really quickly, because I actually want to show you this. Yes, quit. By the way, you can use Control-D if you want to quit an easier way on this stuff. So let's see. What was it? numlist.c, the current version. So we fixed a couple of our stupid bugs, right? Our segfault bugs. Add num is fixed. So we have that problem fixed now. We don't lose values on our reverse function anymore. But notice, empty still is bad, right? While cur is not null, free it, and then access it, right? So, and then we had this interesting question of, well, will this crash or will this not crash? Okay. Well, this is the code. Let's compile it. Make clean all. Num main. No segfault. We deallocated memory and then we accessed it. No segfault. Okay. Take this as a warning. There are a lot of bugs out there in programs that are exactly like this. Program is freed and then it's used. Okay. When I was at Microsoft, I had a friend who worked in the Visual Studio Libraries team, which is kind of well, I would think it was boring, but he had a good attitude about it. He said, when I write a good library function, I make everybody's programs suck less. And I thought, that's a really good view to have if you have that kind of job. But they had an interesting thing where they changed their allocator so that when they released memory, it trampled on a little bit of the memory. You're allowed to do that, right? We talked about that. Once a program has deallocated memory, it's done with it, right? So the allocator can do whatever it wants. Well, all of a sudden, they started getting a bunch of calls from customers saying, we tried out your new version of Visual C++, and our programs crash now. And it's because they had these kinds of bugs in their programs. They would deallocate memory, and then they'd try to access it, but the allocator had changed, so they would trample on the memory a little bit. These kinds of bugs are out there. So how do you find them? This is the question that we want to look at now. So Valgrind is the tool that you can use for doing this kind of thing, at least on Linux and on IA32, because what it does is it actually simulates a processor executing. It's pretty wild what it does. And what it will do is analyze the program's behavior with respect to memory management, and also you can have it analyze its cache behavior and a few other things as well. But basically, it watches your program run and makes sure that it doesn't do anything crazy. Okay. Unfortunately, it was primarily designed to run on Linux. There's no port to Cygwin yet, and there's a port to OS X, but it's a little flaky still. Yet another reason why we prefer Linux for this class. Okay. So the most widely tool in Valgrind is the memcheck tool. It's the one that runs by default. And what this does is it watches your program execute to see if it does anything stupid. Okay. So like I say here, Valgrind also benefits from debugging symbols. If it has them, it will use them, and it will actually give you some really helpful output. Okay. Now, yeah, you usually use Valgrind after you've gotten through all the crashing bugs because, Valgrind can be helpful with some memory issues, but GDB and Valgrind are really used for slightly different things. Okay, so you run it, and you give it your program name, and it starts running. Notice it prints out some information, and then it will tell you when there's actual issues. So let me go back to our little demo again. And so we ran num main. We know there's a bug, right? But it didn't crash. So now let's say Valgrind num main. And notice, so we get the standard output. Valgrind num main, it says, hey, I'm running Valgrind, aren't I cool, right? And then it starts running our program, and it does stuff. But now notice what we have here. Invalid read of size 4 at a bunch of addresses, right? So this is the line of code that did the invalid read. It says address is 4 bytes inside a block of size 8 freed. So we're trying to access memory that was freed. We shouldn't be doing that, right? So it's telling us, hey, this is the line where this is occurring. Okay. And we can go on, and you can see some details about this. Notice heap summary. It says, hey, everything got freed, but you did try to talk to memory that was already freed. Okay. So notice we have 10 errors. So we have some issues with trying to access freed memory. And this gives us a clue. We say, oh, okay, numlist.c34, vi numlist.c, and we go to, oh, hey, yeah, 33 down. And hey, look, we say free cur equals cur arrow next. Well, in this situation, it's obvious now what the problem is. We need to access memory slightly differently than we do. But take note that this program did not crash when we tried to run it, even though we knew there was a bug in it. Okay, any questions on this? This is a little scary, I think. This is why I like using higher level languages, because this kind of stuff is scary, and that's why tools like Valgrind are so useful when you're debugging C code. Like some people will just run their program in Valgrind to see if it produces any errors anyway, which is really helpful. Now, yeah, so if your program does anything bad, Valgrind prints out an error. So accessing previously freed memory, we saw that already, and that it had a problem with that, which was good. Now the line numbers are slightly different because I added that bug line at the top saying this is what the bug was. Because when I give this lecture each year, I have to try to remember what bugs I introduced in what places. So Valgrind will tell you exactly what happened and where, and that gives you some details that you can go use to start diagnosing the source of the defect. Okay? Now, the program will also possibly do other things, and Valgrind will analyze the heap usage and print out details like what blocks were leaked and what pointers were accessed that were invalid. So let's say the num main decided to not call free on its list nodes. Then it will tell you, hey, you lost some memory. Okay? So again, we can see an example of this. So copy num list. This is bad 3 over num list.c. So if I say num list c, then notice now we've commented out the free. Well, now it's not trying to access deallocated memory at least, right? But we have another issue. So I will go ahead and make clean all. And when we say Valgrind num, num main, then we run it and it says, hey, you know what? You lost a whole bunch of memory. Okay. Now what we don't know is where that memory was allocated. We aren't given any hints about that, but it will actually output that information as well. So it's actually got some really useful debugging stuff. If we run with that leak check equals full, then Valgrind will actually tell us where the memory was allocated. It was allocated by add num. So now at least I get a clue as to what thing was allocated that wasn't freed. Okay? This stuff is really powerful. It's really just incredibly useful for writing bug-free programs. Okay? I will not demonstrate that for the sake of time. You can try it yourself. Okay, so yeah, these things are very powerful. Are there any questions about Valgrind? we did a very brief coverage. I mean, you really don't use it in much greater depth than we've talked about so far. I mean, it's able to show you things as well as like you try to access memory that you have not allocated. In fact, one of the students contacted me over the weekend saying, when I run my allocator tester, I get a crash in malloc, or I can't remember if it was that or he got a segmentation fault. And the cause of the problem was that he was overwriting the ends of his mem block. You know, exactly what we were talking about in class. If you try to write outside the payload and you hit a header or you hit a footer or something like that, Valgrind will catch that as well, and it'll say, hey, you're trying to access memory that you didn't allocate. Okay. So anyway, very useful tools. Just wanted to give you a brief demo of both. So this is just sort of the wrap down. Yeah, so GDB is really good for tracking down crashes, especially. It's very good for diagnosing segmentation faults and other defects, especially when you need to actually watch as an algorithm executes, but you don't necessarily want to go in and put a bunch of debug lines. Or when you're debugging assembly code and you can't. And Valgrind is really good for diagnosing those more subtle issues that may still be there even though you've gotten rid of all your crashing bugs. So Valgrind is usually used as the second step after you've gotten your GDB stuff sorted out. Okay? So you want to make sure you use the right tool for the job. Any questions on this? All right, well, that is all I have. I hope this was helpful. And like I said, I'll get these posted up for everybody. And hopefully this will make your lives a lot easier in CS24 and then other classes after that. Because if you know how to do this stuff, you're going to save yourself a ton of time.